Well, one more thing that I want to show you folks before I take you to the notes. So one of the first things that we're going to be discussing in this note packet is what a function is. And it's kind of a very broad, generic sort of definition. Doesn't really like paint the picture, immediately. Of course, we're going to look at examples of functions, and there are a variety of ways that they can be presented to us. One of my favorite applications of a function is with one of these guys. All right, and that right there is an Xbox One remote, and one of my favorite games to play on Xbox One. And if I got any fans in here, feel free to light up the chat. But Mortal Kombat. So, you guys might be familiar with characters, Scorpion and Sub-Zero, right? But yeah, one of the games that I picked up last year, maybe it was even before that, I can't remember exactly when it came out, but was Mortal Kombat 11, and I've actually been playing the Mortal Kombat video games since the very first one came out. I was probably too young to start playing it, to be honest with you, but I was hooked ever since. Yeah, exactly. Finish him, right? But the reason why I bring this up, there's a way of connecting video game controllers to functions. So for any of you that are familiar with playing Mortal Kombat or just really any video games, game controllers have all these buttons on them, and each button is designed to do a special function in the video game. So for example, in Mortal Kombat, I believe this button on Xbox One will make your character do like a high kick, and this button down here will make your character do a low kick. And then we have like your different punches that you can do. Of course, you can do some blocks up here, and you can amplify your moves or whatever. But basically, every button is programmed to serve like a single function. It makes your character do one specific thing. Now, that's not to say that you can't have multiple buttons making your character do the same thing. There are some video games like maybe Sonic the Hedgehog where maybe both these buttons make Sonic jump. But regardless, one button is supposed to do one action in your video game. And that's kind of the essence of what a function is a function will take a value and assign it to one and only one value. And that's what we're going to be seeing, especially on the first page. And then we'll get into all the nitty-gritty of what we can do with functions, certain characteristics of them, and then we're going to finish off the notes with something called the difference quotient, which if you plan on moving up through the math sequence and perhaps encountering Calc 1, this difference quotient is an expression that you'll be working with quite extensively. So I get to get your feet wet with that. All right, so without further ado, let's go ahead and put the fun in functions, or maybe the fun in dysfunction, who knows. Alrighty. So when I said I wanted to mix things up and give you a little bit of a break from the norm, I definitely mean that. You look, our notes have a little bit of a style to them, at least for this section. I wanted to get a little more visual and sort of condense some items down, give us room for plenty of practice, and so on and so forth. But up here, a function is a relation that assigns what's called an input to exactly one, and that's key here, exactly one output. All right, so you can think of like the different buttons on a game controller as like the set of inputs, and then whatever action takes place once you press that button would be a particular output. When we take the set of all inputs and we collect all the possible inputs, that gives us what's called a functions domain. Okay, so all of the buttons that you can press on the Xbox remote, when you collect them all together, they make up the domain of that controller. We can also consider the set of all outputs. Anybody have an idea of what this might be called? You've worked with functions before? The range, you got it. So if we look at all the possible actions that these buttons force the character on the screen to do, the set of all those actions is called the range. Now, all functions have a domain and a range, but due to the variety of functions, as well as how they can be presented to us, some functions will have a different domain than others. So keep that in mind. We're going to move on to look at some of the ways that functions can be presented to us. We'll start with mapping diagrams, which those are a nice visual of seeing how inputs are assigned to outputs. Ordered pairs, functions can be presented to us that way. Functions can also be presented to us as equations. They can also be presented to us as graphs. And then there are a few other ways that they can be presented, but the ones that I included here are probably the most common ways of doing it. Let's start with a mapping diagram. This is from our textbook. So this is actually some menu items from McDonald's. And my theory is that the author didn't want to study Burger King menus because of the whole Burger King foot lettuce stuff there. But anyhow, that's neither here nor there. But here we're seeing sort of a correspondence between different menu items from McDonald's and prices. The menu items, which are being assigned to these corresponding prices, these would be considered the input of a function presented this way, and then the different prices would consist of all the outputs in this scenario. And what I want to point out is that each individual input or each individual menu item is being assigned one and only one price. So for example, the cheeseburger, according to this mapping diagram, corresponds or is related to the price of $1. It doesn't get any other prices. Okay, it's just this one and only one price amount. The sausage biscuit is being assigned only one price as well. Apparently, that would be the same price as the cheeseburger, which is totally fine. Okay, you can have a variety of items being the same cost at a restaurant, much like you could have a set of buttons doing the same action in a video game. What you want to look out for are any menu items that are being assigned to different prices. So for example, let's say that the sausage biscuit was assigned a price of $1, but was also assigned a price of $2. That would break the rule of a function, because a function is supposed to take an input and assign it one and only one output. So if you see like an input being assigned to two different outputs, you don't have a function. All right. Looking at the bacon McDouble, can't say I've had one of those, by the way. That's being assigned one and only one price, $2. And then we have the triple cheeseburger and the classic chicken. The cheeseburger is being assigned one and only one price, and so is the classic chicken. So as you can see from a mapping diagram, we can have multiple inputs going to the same output, but that's okay as long as we don't have any one input going to two or more different outputs. So I want to make a note on that. Based on this mapping diagram, no input is assigned to 2 or more outputs. And what this means for us, and this is a symbol I'm probably going to use quite a bit in this section. This is a mathematical way of saying that this implies. What this implies is that this mapping diagram would be an example of a function. Okay, it satisfies the definition of an input being assigned one and only one output. We can also talk about this mapping diagram's domain, which I'm going to write as capital D. And unless your function is presented as an equation or graph, you'll write the domain using set notation. And set notation is what's actually being used in the set of ordered pairs example. But the domain would consist of a list of all the inputs. So you could literally write the word cheeseburger in your set notation, and then the sausage biscuit, and then so on and so forth until you get to your classic chicken. And that would be the domain of this function. The range, which I'll indicate by capital R, would consist of the different prices. So $1, $2, and $3. So far, so good? Rock on. Okay, so let's look at the other way, or another way that functions can be presented. They can be presented to us as a set of ordered pairs. And the easiest way of determining whether or not a set of ordered pairs is a function is to pick out what your x values are as well as what your y values are. But between those two variables, it's the x values that are really telling of whether or not a set of ordered pairs is a function. So here's how I typically denote it. Looking at the first ordered pair, 1 is the x value, 2 would be the y value, and then so on and so forth, 3 and then 4, 5 and then 6, 7 and then 6, and then 8 and 7. If you look at the x values that are involved in this set, none of these x values are repeated, which implies that regardless of what x value you are in this set, you're being assigned only one output. Okay, so for instance, with the x value of 1, this x value of 1 shows up only one time in this set, and it's assigned the output of 2. You don't see an x value of 1 anywhere else. If it was anywhere else, then it's likely that x equals 1 is being assigned 2 different outputs or more. Likewise with 3, that's only showing up once in this list. So is 5, so is 7, and so is 8. So I'm going to make a note similar to the last version of a function. I'm simply going to put no repeat x values. And if that's the case with a set of ordered pairs, then you have a function. The domain would be the set of all the x values here. So we're going to open up some set notation, and we're just going to list the x values. We're not going to write ordered pairs. We're just going to list the x values separated by commas. So 1, 3, 5, 7, and 8. The range would consist of all the y values. And if you have any y values that are repeated, you only need to list it one time. Case in point, 2, 4, 6, and 7. Now I want to let you know that it is possible to create a mapping diagram for a set of ordered pairs. I'll show you how to do that real quickly. I'm going to try to emulate the mapping diagram that was in, towards the left here. I'll have a box for the inputs and a box for the outputs. And in this left box, I'm just going to write out all the numbers of the domain, going from top to bottom, 1, 3, 5, 7, and 8. Okay, that would be our domain, so I'll put D there. And then our range would consist of the numbers 2, 4, 6, and 7. And to wrap up this mapping diagram, you can look at the ordered pairs and just see like how the x values are being assigned to y values. So in the first ordered pair, we have 1, 2. So that means 1 is being assigned a y value of 2. So I'm going to draw an arrow from 1 to 2. 3 is being assigned a y value of 4. So I'll draw an arrow from 3 to 4. 5 is going to 6. 7 is going to 6. And then 8 is going to 7. And even though we have kind of like a repeat in y value, that's okay. Y values are allowed to repeat. As long as the x values don't repeat, you have a function. So you can see that regardless of what number you look at in the numbers with the domain, they're only being assigned one element of the range. Okay, so every input is being assigned to only one output. And that's kind of a visual verification that we have a function. Moving on. So another way that a function can be presented to you is by way of an equation. And if you're able to determine that your equation is a function, which the easiest way to do that is by something called the vertical line test, which I'm actually going to go over with the very last representation. If you're able to establish that your equation is a function, then what we do is we swap out the variable y with a special notation. It's called function notation. I know, earth-shattering, right? And the way that function notation is presented, typically with the lowercase f, and once we write f, we open up a set of parentheses, and inside the parentheses we put the variable x. All right, have we seen function notation before? Nice. So you're not really restricted to using f and x as the letters with function notation, as long as it has this format where it's a letter parentheses x. That's indicative of function notation. So you could have something like lowercase g of y, parentheses y, but as long as it satisfies the format, like you're seeing here, then it's function notation. That replaces the variable y, so instead of y equals that fraction, we're going to write f of x equals that fraction. And that would be the function notation version of the equation. And function notation is really meant to be user-friendly. And here's what I mean. I'm going to give you an example of how this works. Let's say that I wanted to consider an x value of 5. If I wanted to plug 5 into the fraction x plus 3 over x minus 4, function notation would help us to see that we actually wanted to plug 5 into x. So if you see f parentheses 5 like this, we would read it as f of 5, and it does not mean f times 5. This is actually asking us to take the number 5 and plug it into all of the x's that are on the right-hand side. So for example, we have x plus 3 over x minus 4. With the x value of 5, that's going to replace all the x's in this fraction. So if we see something like f parentheses 5, then we're going to modify the expression that's using x simply by plugging 5 into wherever we see the variable x. And then we just kind of stick with, what's on the right-hand side, and we funnel it down into, its most simple form. Case in point here, we could add 5 and 3 in the numerator to get 8. And on bottom, we could do 5 minus 4, giving us 1. And so by plugging 5 into the function, the number that we get is 8. And so what this implies is that f of 5 is equal to 8. I'm going to bring in some of the earlier language. This value of 5 is a particular input. And this value of 8 is a particular output. And there's only one output that we're getting when we use x equals 5. And that should be expected because a function assigns an input to exactly one output. Something else I'd like to add here is what this means from a graphical perspective. If we have a statement such as this, f of 5 equals 8, it means a particular point would be on the graph of this function. And the point would have the following ordered pair. It'd have 5 as the x-coordinate and 8 as the y-coordinate. So basically, when you plug x values into a function, what they generate are y values. And you can always create an ordered pair by considering the input and its corresponding output. All right, is this all making sense so far? All right. Now, as for its domain, we'll actually discuss this in greater detail later on. But for now, one way of establishing the domain is to figure out what we're not able to plug into the function. And the key to this particular type of function is to examine the denominator. Would there be a bad value of x for this function? In other words, is there anything that we could plug into x that might create issues for us? Yeah, x equals 4. So looking at this denominator, if we were to plug the x value of 4 into it, we would get division by 0. So we want to steer clear of that x value. I'm just going to note that x cannot equal 4. Any other x value can actually be plugged in because it's only 4 that creates division by 0. So one way of packing that all in together notationally is to use set notation again, but the format of it is going to be a little bit different since this is not a set of ordered pairs or a mapping diagram. One way to write out this domain using set notation is to open up a set. You can write the variable x and then this vertical bar. And what this vertical bar represents is the set of all x such that, and to the right of the vertical bar, we put the conditions on x that we wish to uphold here. And the condition on x is that x cannot equal 4. So I'm going to write x cannot equal 4 and then close off the set notation. You could also give the domain an interval notation. And the way to do that is to construct a number line with this bad value of x on it. So I'll put 4. And since this is the only value of x that we can't plug into the function, what that means for us is that any x value that would be to the left of this number, all the way down to negative infinity, can be used. And I'm going to use a parenthesis on 4. A bracket would imply that you could use 4. And since 4 is the only number that we can't use in the function, that means any x value that's larger than 4, or to the right of it on the number line, can be used as well. And for similar reasons, I'll put a parenthesis on the 4 pointing towards that shaded part of the number line. And what you would see is that the interval notation actually has 2 different intervals involved. The first interval is that from -infinity to 4. Then the other interval would be from 4 to infinity. And then we would just union them to just form a cohesive set. So that would be the interval notation of the domain. As for the range, the easiest way to do the range is to actually look at the graph of this function. And we won't do it for this function because I actually have to kind of like hold off until we get to section 3.2. So that's a skill that we will mainly focus on in section 3.2, is finding the range of functions based on their graph. So I'm just going to put it this way: for the range, you need the graph. So we're going to hold off on finding the range for this function until we learn how to do that. Any questions so far? All right, the last way a function can be presented, or at least the last way I'd like to cover, is by a graph. And this is a graph from our textbook, which is related to a bike ride. It says Caleb rides home from his friend's house on his bicycle. The graph below shows his distance d from his house after m minutes. So you can see the horizontal axis, it's kind of rescaled. It goes from 0 to 30. At least that's how much they wanted to mark. And it's no longer the x-axis, but instead it's the m-axis. And so they're using m in place of x. All right, I think it's a more relevant variable to use since the x-axis stands for time in minutes. And then they also relabeled the y-axis as the d-axis, because all the y values would correspond to particular distances. Now, how we would know that this is the graph of a function is by using something called the vertical line test. And basically, the vertical line test says this: draw any amount of vertical lines through your graph and keep track of how many times it crosses the graph. So with this vertical line that I just drew, it only crossed the graph in one spot. I'm going to draw another random vertical line, maybe right here, and that only crosses the graph in one spot as well. Do you think this will always be the case, that we draw a vertical line and it crosses the graph in only one spot? Well, actually, yeah, anywhere you draw a vertical line through the graph, it's only going to cross the graph in one spot. So, a few more vertical lines could probably convince us of that fact, right? This is actually good enough for me, but if you want one more, maybe we could do one over here that would cross the graph in only one spot. And if you get the sense that all vertical lines you draw through the graph cross the graph in one and only one spot, then the graph actually passes the vertical line test. So I'm going to make a note here. I'll say the graph passes the vertical line test, which, if you're okay with it, I'm going to write that as VLT. And what this implies about the graph is that it's the graph of a function. And if you think about it, there's only one output for each input that you could consider. So our inputs are those that are on the horizontal axis, the m-axis, and our outputs are those that are y-coordinates on the graph. And I'm going to get rid of these vertical lines for the next part. but there's no input that's being assigned 2 different points on the graph. Every input is being assigned only 1 point on it. So that means every x value is being assigned only 1 y value, or m and d if you want to use those. Now, there is a way to figure out the domain for the graph of a function, and we're going to spotlight that more in section 2. For now, what I would do is look at the smallest x value being used and the largest x value being used, or in this case m. And the graph actually starts at this point right here, and whatever x value corresponds to this point would be the lowest value of our domain, and that x value would be 0. So I'm going to write 0. And you actually use up all the x values from 0 going up to 28 on this graph. And so what I just shaded on this horizontal axis is a kind of a visual of the domain. And these x values go from 0 to 28. Okay, that's the largest x value on the graph. So I'm going to write comma 28. And because this graph has endpoints that are filled in, this was a point on the graph at 0, 2, and then this point is on the graph, 28, comma 0. We can actually include these 2 x values. And so we would put brackets on 0 and 28 in this case. And I'll kind of spoil some of the details from section 2. We kind of handle the range in a similar way. We look at the smallest y value on the graph and the largest y value on the graph, or in this case, d values. So can anybody maybe offer like what the smallest y value on this graph is, or what the smallest y coordinate is? 0, exactly. And we're going to include that. That y value is part of a y coordinate of a point that is officially on the graph. It happens right here. And then for the largest y value, we want to look at the highest point on the graph, which appears to be right here, that peak. And the point isn't like explicitly stated for us in the sense that it doesn't label the x and y coordinate for this point. So we'll probably have to approximate that. And to start that out, I'm just going to draw a little dashed line over to the y-axis and just kind of approximate, where that, or what that y coordinates value would be. And for all, for sake of simplicity, maybe we could say that that's 2.5. If we had more information, we could be more specific, but I'm just going to say that the largest y value on this graph is about 2.5. So I'm going to write 2.5 and put a bracket on it. All right, so there we have it. Lots of info here. So if you want to just kind of review, just kind of glance through everything here, let me know if you have any questions. I'll be happy to go over those right now. Otherwise, we'll move on to the next part. You guys ready to move on? Here we go. So this next page is going to give us more practice with finding outputs for particular inputs. The first three parts of this example give us inputs that are specific x values, particular numbers for the value of x, whereas the remaining parts of the example don't have a particular value of x, but want us to modify the function by either multiplying the function by a number or plugging in some sort of variable expression. So we'll see how to handle that in just a moment. But I want to remind you that with notation such as this, it's function notation, And if we see a particular value of x inside of it, in this case, it would be x equals 0. Function notation just tells us to plug in 0 into all the x's. And what I mean by that is all the x's that are part of this expression, 4x squared plus 3x minus 3. So we're going to plug 0 into the x that's being squared, as well as the x that's being multiplied by 3. And we'll simplify it down into a single number, and we'll get our output. So this would be 4 times 0 squared plus 3 times 0 minus 3. 4 times 0 squared is going to simplify to 0, so is 3 times 0. But we still have this minus 3, and the end result of all this would be negative 3. And that would be our output. Okay, so we could write this more succinctly. F of 0 is equal to negative 3. Let's go ahead and plug 3 into the function. That's going to be 4 times 3 squared plus 3 times 3 minus 3. Now, if you're going to simplify this by hand, you want to follow the order of operations. And PEMDAS would tell us to square the 3 first. So the first term turns into 4 times 9. If you want, we can probably knock this out at the same time. 3 times 3 is 9 minus 3. So we're looking at 36 plus 9 minus 3. That's going to be 45 minus 3, giving us 42. That would be our output. All right, you don't always have to write the more compact version of what this problem implies. This will probably be the last time I do it, actually. So the fact that we got 42 when x was 3 means that f of 3 is equal to 42. You guys want to take care of part C, and then we can work on the rest together. All right, I'm going to go ahead and jot my work down. Let's see if we line up. $24. Sweet. Okay, well, let's move on to D, E, and F. We're not taking a specific x value and plugging it in. Rather, we're modifying the function itself. In part D, when you have a negative in front of the function notation, what this means is find the opposite of the function. Now, algebraically, here's what it all boils down to. We're just going to take negative 1, and we're going to distribute it to the expression from right here. Okay, so basically, negative f of x means multiply your function by negative 1. And here's how we can set that up algebraically. And what we'll do is we'll clear parentheses by distributing -1 to all three of these terms to get minus 4x squared now, minus 3x, and plus 3. And if there's nothing more that you can simplify, which I'm not seeing anything here that simplifies further, this is where we would stop. And so part D is an example of where we're modifying the function. And in this case, we're modifying the function by multiplying it by -1. And if you want to think of it this way, this would be our output from doing such an operation. Now for E, we're seeing a negative sign again, but this time the negative sign is with x. So how you want to handle this is by changing all of your x's to -x. Okay, so maybe let's note that. Actually, you know what? I'm going to write it this way. Substitute -x into x. So instead of 4x squared, with this substitution, it's going to be 4 times, and you want to use parentheses for this, 4 times -x squared, plus, instead of 3 times x, it's now going to be 3 times -x, and then our minus 3. This does simplify. You may recall from chapter 2 that if we square a negative variable, it becomes positive. And so this entire first term simplifies to 4x squared. If we multiply positive 3 by -x, the middle term turns into minus 3x, and then nothing's happening really with our last term, so we'll just carry it back down. And this would be our output should we plug in an input of -x. And so here we get another expression as our output. Okay? Now with part F, x has changed into the expression x plus h. And so we do a similar thing, something like this. We're going to plug x plus h into x, or substitute x plus h into x. So here's how you want to write it out. 4, and remember we're subbing in the expression x plus h into x. So instead of 4x squared, it's going to be 4 times x plus h quantity squared, plus 3 times quantity x plus h again, minus 3. Does that make sense? Now here's how we're going to simplify. All right, roll your sleeves up because there's going to be a lot of simplification here. I'm here to help guide you through it. We're first going to FOIL the x plus h. And just to keep things organized, I'm going to write the 4 down and then a set of brackets. And inside the brackets, I'm going to write out 2 factors of x plus h. I'll close off the brackets, plus 3 times quantity x plus h, minus 3. Now the reason why I wrote out 2 factors of x plus h is just to remind us that a power of 2 on an expression like this means that we're to FOIL. Okay, so I'm going to give you the next 30 seconds or so to FOIL out the x plus h expressions, and I'll show you what I got, and we can go over any questions afterwards. Once we're all good to go, we'll wrap up the rest of this problem. All right, so go ahead and see if you can FOIL out the x plus h expressions, simplify it as far as possible, and we'll pick back up in about 30 seconds or so. All right, so after FOIL, we should have x squared, and then there are two copies of the expression x times h, right? So we have x times x for giving us x squared, but then we have x times h, and then another x times h. So there are two copies of the expression xh. And last but not least, we have the h times h to give us h squared. And is anybody wondering WTH about what I got? All right, just mess with you about the WTH. But are we lined with x squared plus 2xh plus h squared? All right, cool. Now what I'm going to do is also distribute the 3 to clear parentheses. It gives us 3x plus 3h, and then this minus 3. We still have brackets though, so in this next line of math that I'll do, we'll want to distribute 4 to clear the brackets. We end up getting 4x squared. 4 times 2 gives us 8, so 8xh, and then 4 times h squared gives us 4h squared, and then plus the rest. Now, believe it or not, with all these terms, we actually don't have any terms that are like terms. So what that means is there's no further simplification that we have to do here. For example, there's no other term involving x squared, nothing else involving the product xh, and so on and so forth. So this is what results when we plug x plus h into the function. All right, any questions about any parts of this example? All right, let's knock out the example on the next page, and then we'll take our break. So we saw a real-life application of a function in a graph format. The time and how far away I think it was Caleb was away from his house on his bike ride. What we have now is a real-life setting in which a function can be applied as well. This time the function is in equation format, and there's actually two that they provide us with, and we're going to use these two functions they provide us with to construct a third function. It says here, suppose the revenue R in dollars from selling X cell phones, which the units that they're using in cell phones is hundreds, is given by this function, capital R of X, so that's function notation, equals negative 1.2x squared plus 233x. They move on to tell us that there's a cost function. Of course, it costs money to sell things, right? So their cost is given by a function, capital C of x equals 0.08x cubed, and so on and so forth. So these two equations are functions, and if we wanted to, we could start picking and choosing particular values of x and plug them in to figure out revenue, how much money is brought in from those sales, as well as the cost, so how much it costs to actually sell that many cell phones. In part A, they want us to construct what's called a profit function, so this would be the money left over after you subtract off the costs from your revenue. And it's really straightforward. It's a straightforward process because let's first write P of x, and what we do is we substitute the equation for each of these two function notations. So I'm going to replace the function notation R of x with the expression negative 1.2x squared plus 233x. And from this expression, we're going to subtract the expression 0.08 x cubed and so on and so forth. Now, this is where it can get, this is where you have to be careful. When we're subtracting an expression that has 4 terms in it, such as this cost function, we want to be sure to use parentheses, or you can even use brackets if you want. For some reason, I use brackets with these types of problems. So in other words, make sure that you put whatever function that you're subtracting inside of some sort of grouping symbols. That's particularly important for this type of problem because we're subtracting. So by putting the expression in some grouping symbols, it cues you in as to needing to distribute the minus sign, which is what we'll have to do. All right, so inside of the brackets here, 0.08 x cubed minus 2x squared plus 40x plus 250. And we'll proceed to distribute the minus sign to every one of these terms. That way we can release that expression from brackets. Negative 1.2 x squared plus 233x. Okay. The 0.08 x cubed turns into minus 0.08 x cubed now, plus 2x squared minus 40x minus 250. And from here on out, you just want to combine like terms as well as write this expression in standard form. So, reorder it so that your highest power goes first, and then your next highest power, and so on and so forth. So when I'm looking at this, the term with the highest power is negative 0.08 x cubed. So I'm going to write that as my leading term. There's another term in this expression that can combine with negative 1.2 x squared, and that would be positive 2x squared. Okay, the reason why I'm looking at those terms is because that would be the next highest power of x, and what you would get after you combine those two terms is positive 0.8 x squared. Is there anything that 233x can combine with? Yep, minus 40x. And when you combine those two, you should get positive 193x. And then last but not least, we have this minus 250, which doesn't combine with anything. So we'll just copy it back down. And that would be our profit function. And the way it works is that we could choose any value of x and to plug it into this function, okay, all the x's, and that would tell us what the profit is from selling that many cell phones. So this is our answer to part A, and part B actually wants us to do just that. Part B wants us to find the profit when x is equal to 15, meaning 1,500 cell phones. So in other words, they want us to find P of 15. And I'm going to leave this up to you folks, okay? Take 15, plug it into all of the x's that are present in our profit function, and you can use your graphing calculators to simplify the arithmetic if you want. And in about a minute or so, we'll see what we get, and we'll interpret it, and we'll take our break, okay? So I'll check in on you guys soon. Okay, anybody want to offer in the chat what the corresponding profit is for 15? Bingo, got it. Yep, 2,555. All right, and that would be in terms of dollars. And that gives us a way of answering part C now. So based on part B, we just learned that P of 15 equals 2,555. Now, what this means is that the profit from selling 1,500, okay, because our X values are in terms of hundreds. So the profit from selling 1,500 cell phones is 2,555. Make sense? Okay, so let's go ahead and take a 5-minute break. When we come back, we will look at how to determine the function, determine the domain of a function algebraically. So that's when functions are given to us as equations. We already had a preview of that, by the way. And then something called the difference quotient. So this is that whole calculus topic that I was shedding some light on at the beginning of class. So I'll see you guys in about 5 minutes. We'll go ahead and take care of the rest of section 3.1, and then we'll move on to do some practice in the form of group work. All right, so see you soon. All right, folks, let's go ahead and pick back up with the rest of the notes for section 3.1. And then we'll spend the rest of class working on some practice problems, which I just put together and uploaded into the 3.1 folder. So when the time comes, you and your team will be able to access the practice problems I had in mind for the rest of class today. And basically what's going to happen is I'm going to split you off into like some breakout groups, and you guys can collaborate on solving the problems that I put in the file. And I'm going to bounce between each and every one of the breakout groups to check on you folks and answer any questions that you have as they come up. All right, so that's heading our way as soon as we finish determining the domain of functions algebraically as well as the difference quotient. Okay. So when functions are presented to us as equations, the best way to approach finding the domain is to figure out what values of x should not be plugged in. So, long story short, we can assume that the domain of a function, when it's given as an equation, is all real numbers except or excluding values of x that cause one or both of these things. Division by 0. Okay, so if there are any values of x that create division by 0, we discard them. Okay, and if there are any values of x that create negatives inside of an even root, we discard those x values as well. And as soon as we've thrown out all the bad values of x, what's going to be left over from the set of real numbers would be the function's domain. And by the way, what I mean by even root, here's an example, would be something like the square root of a negative number. Okay, so if there are any x values that create negative numbers inside of a square root, then we don't include those as part of the domain. So I have a few functions here where we're going to get some practice with this. Our first function is x plus 5 over x squared minus 9. Now we don't have to worry about the second bullet point where there's an even root because the function in part A doesn't have any radicals whatsoever. But what we should probably worry about is division by 0 because in our denominator we have the variable x. And the way to figure out what x values would create division by 0 is to take this denominator's expression, x squared minus 9, and set it equal to 0. And we end up setting ourselves up with an equation that we could solve. And one way that you could solve for x here is to factor the left-hand side as a difference of two squares. And as we've done in the past, we could set each factor equal to 0 and solve for x. So one value of x is negative 3, and another value of x is positive 3. Now, these two values create division by 0. So what that means is, in the context of the domain of this function, we actually don't want these x values. So I'm going to jump to this version of our solutions. I'm going to say we don't want x to equal negative 3, and we also don't want x to equal positive 3. Does that make sense? Because if you plug these two values into our function, they would give us a 0 in the denominator. Does that make sense? Now that means any value of x that is not negative 3 or positive 3 is okay to use. So if we're assuming the domain is real numbers except for these two, then that means there are lots of other values of x that would truly make up the domain. The easiest way to figure those values of x out is to draw a number line and put the bad ones on there -3 and +3, and then shade the parts of the number line that are separated by these two numbers. So we're allowed to use anything to the left of -3. I'll put a parenthesis facing that shading. We can use any x values between -3 and +3, and we can also use any value of x that's larger than 3. And so you'll notice that it looks like the entire number line is shaded, but it's not really, because we put -3 and +3 on there, and we're using parentheses on those two values, meaning that we're not including them. And so this domain would be made up of 3 different intervals. The first interval, -∞ to -3, we'll union that with the middle interval, -3 to +3, and then we'll union that with the interval to the right of +3. And this would be our domain. And so that represents the set of all values that you could actually plug into the function. All right, and this interval notation indicates that both -3 and +3 are actually being excluded. Visually, they're kind of being skipped. So any questions about that? Now with part B, we probably should worry about the second bullet point, because we have a square root. Specifically, we got the square root of x minus 2. Now, there are definitely going to be some values of x that we shouldn't be plugging into this function. Can anybody think of a value of x that we probably can't plug in to the function g of x? We could plug 2 in, because the square root of 0 exists. But right, -2 can't be plugged in, because if you look at g of -2, that gives you the square root of -4. Now, we know this simplifies to 2i, but we only consider the real number outputs for a function, because when we go to graph functions, we can't really graph y values that have i's with them. So, in this case, we don't want to use -2, and there's actually a whole lot more than just -2 that can't be plugged in. So here's the trick on how you do it. We actually focus on the expression that's on the inside of the square root. And as long as the square root is not in the denominator, which it's not in this case, we take that expression and we set it greater than or equal to 0. Okay, this is saying that we want only the x values that make the inside expression positive, but it could also equal 0 because the square root of 0 exists. Now this is a little bit of a different setting than part A. We're kind of in an inequality setting, and we basically just solved the inequality like we were doing before. In this case, we'll isolate x by adding 2 over to the right-hand side, and this tells us that the only x values we're allowed to use are those that are greater than or equal to 2. On a number line, since we're comparing x to 2, I'll put a tick mark for 2 on the number line, and we'll shade to the right of it. Now, since there's a bar with this inequality symbol, we will also include the 2. And so our domain would be bracket 2, comma, infinity. Okay, so that's the approach for square roots. Now, if the square root is in the denominator, you don't want to include the 2, okay, because remember what 2 creates. G of 2 gives us the square root of 2 minus 2, which is the square root of 0, which gives us 0. So if this were maybe written as 1 over the square root of x minus 2, then we would have to use a parenthesis on the 2, because that would create division by 0 in addition, to everything else that's going on here. So just a little heads up on that. And I include stuff like Part C because domain can be one of those skills where, the problem looks too easy, so easy that it can, kind of make itself complicated. But for Part C, there's no way that we could divide by 0. Okay, there's no x in the denominator of a fraction. Really, there's no fraction here unless we forced one. But there's also no radical symbol. So with an expression such as 2x plus 3, there's no division by 0 possible. And at the same time, there's no square root of a negative possible. So what that means is that we can use any value of x from the number line as an input for this function. Any value of x that we plug in will give us a legitimate y value. And so if we draw a number line, that would mean we'd have to shade the entire thing. Okay, and every number that I've shaded on this number line would be a valid input for this function. And the shading technically goes from negative infinity to positive infinity. And we would construct the interval notation accordingly. And what would be a way of kind of like wording out this answer for the domain? The domain would be the set of all real numbers. Yep. Okay, do you guys have any questions about any parts here? All right. So the last leg of 2-word Intro to Functions comes courtesy of none other than Sir Isaac Newton. He used this particular expression to come up with what's called a derivative. It's a common topic in Calc 1 and beyond. And I wanted to look for a funny meme involving Isaac Newton. And I'll tell you what really makes this meme funny. Not the fact they, OG thug lifed him, but rather, the thing that's really confusing is the grammar in this meme. And I was joking with my son about it. It says, makes calculus so the next generation suffers massive confusion. And I think that causes a little bit more confusion than, the concept here. But anyhow, Isaac Newton and another dude are credited for inventing calculus. And one of the, primary tools in calculus is based on this item here. It's the difference quotient. And the difference quotient is designed to give us an expression which, when certain values are plugged in, would give us the slope of what's called the secant line. And I feel bad for my sister because she can't really remember all this, but anyhow, a secant line is a line that connects 2 points on a graph, and in this case, the secant line is connecting these 2 points on the graph of what would be a function. And if we look at the x and y coordinates that are represented on the axes, the lower point has an x coordinate of x. I'll mark it this way. And to get the y value, remember we plug these inputs into the function and what they simplify to give us the outputs. In this case, generically speaking, the output would be f of x. For the higher point of the secant line, they're writing out the x coordinate generically. We'd probably have to add a little bit to x to go further to the right on this number line. So they're indicating that little bit by the letter h. And so if this is the generic x coordinate for this higher point, then we would plug this expression into the function to get its corresponding y coordinate. In other words, f of x plus h. And what I want to, the point I want to drive here is that the slope of the secant line is really just a special adaptation of our formula for slope that we looked at in chapter 2, where it was y2 minus y1 all over x2 minus x1. And in this diagram, we can label just regular x as our x1, and then x plus h as our x2, which means that f of x would be our y1, and f of x plus h would be our y2. And if we plug all this into our original formula for slope, we get an expression for what's called the difference quotient. And it goes something like this. F of x plus h minus f of x, and all that is on top of the letter h. Now, due to where h is at, you'll usually see a little restriction on it, particularly h cannot equal 0, I think for obvious reasons. But I just want to mention, why it's called the difference quotient. In the numerator, we're subtracting, okay, hence difference. And the word quotient comes from the fact that this subtraction is part of a fraction, all right? And quotients are linked up with fractions, so difference quotient. And usually what we get from a difference quotient at this particular point, in our math sequence, is just an expression involving the variables x and h. Sometimes you get, a single solid number, but don't be surprised if you're working a difference quotient problem and you get, kind of a generic looking expression as your answer. As we're going to see with our very last example, here we have the function f of x equals x squared minus 3, and they want us to use the definition of the difference quotient to figure out what x squared minus 3 would turn into. I want to mention that there are 3 major components to the difference quotient. The first component is the expression f of x plus h. And that's actually the first thing we'll do. We'll have to figure out what the function turns into when we plug x plus h into all the x's. What we do with that expression is we subtract the original version of the function. That's going to be our step 2. And once all that's cleaned up, we divide everything by h. All right, you ready? Here we go. So f of x plus h. So as we saw earlier, what we're going to do here is we'll take x plus h and substitute it into wherever we see x. So instead of x squared minus 3, it turns into x plus h squared minus 3. And recall that if we have a power of 2 on the x plus h expression, it means FOIL. And you may recall that when we FOILed out x plus h squared, we got the expression x squared plus 2xh plus h squared. Now, don't forget that there's this minus 3 that's lingering on, on the tail end of this, so we'll have to include that in the expression x squared plus 2xh plus h squared. And you'll notice nothing combines, so this is about as far as we could go with f of x plus h, which means we'll move on to step 2. And step 2 tells us to subtract the original function from what we just got in step 1. So here's what I'm going to do. I'm going to rewrite what we got in step 1. And I'm going to subtract the original version of the function, which has 2 terms, reason for brackets here. And I'm going to distribute the minus sign and combine like terms. So we get minus x squared and then plus 3. And what are you guys noticing in terms of, simplification with this current line of math? Does it simplify? It definitely simplifies, okay? X squared and minus x squared are involved in the mix. They actually cancel since they're opposites of each other. And a couple other things cancel. Anybody want to maybe type it in, like what else is going to cancel here? Yep, the negative 3 and the positive 3. So you're left over, or you're left with the terms 2xh plus h squared, which takes us to the third step. We're going to take what we just got in step 2, and we're going to divide it by h. Now check this out. We can break this up into 2 fractions with a common denominator of h. The first fraction would be 2xh over h, and then the second fraction would be h squared over h. And does anybody see why I may have split it up into 2 fractions? What's going to happen with each of these fractions? They're going to simplify, aren't they? It's like in the first fraction, the h's cancel, leaving us behind 2x. And then with the second fraction, division by h is going to reduce the power of 2 to a 1. And so we get something left over with that, and that would be just h to the first power. And that's about as far as we could go. No like terms, no further division. And as I mentioned before we started this problem, don't be surprised if at the very end you get some sort of expression involving the variable x and h. That usually happens with the difference quotient problem. If you're planning on taking calculus, you will move beyond this point and do a special substitution into one or both of these variables. But at this level, this is where we stop. We just adapt the function to the difference quotient definition, and then we just simplify as far as we can. And in this particular case, the furthest that it simplifies to is the expression 2x plus h.